kind of a Star Wars meets physics thing. Today's May the 4th. So, May the 4th be with you. What?
My fold and your shirt look the same color.
Huh?
Your shirt and mine fold like the same color.
Okay. Kind of random, but okay. All right. All right, so let's chit chat about all these problems. So on number 2, because this problem number 2 combines a whole bunch of different things. So here's this pendulum, and it's already moving, okay? It's already moving. So here's the bigger idea, and you've got to keep track of when can we talk about energy and when can we talk about momentum. So up here, it has 2 types of energy. It has UG and it has a certain amount of kinetic energy. When it gets down here to the bottom, it's all kinetic energy. And some of you are so wrapped up in, oh, what equation am I going to use? The test tomorrow is going to be an absolute train wreck. It is. It is going to be a train wreck. If your first thought is, what equation am I going to use, tomorrow's test will be horrible. I'm going to tell you this straight up. But if you step back from the problem first and go, what's actually happening? Oh, it's already moving. Yeah, right. It has potential and it has kinetic energy. Yeah, right. When it gets down to the bottom, all that's kinetic. So if you get out of this mindset that says, oh, I'm going to go straight to an equation. If your mindset is tomorrow, the first thing that you think of is what equation I'm going to use, it's going to be horrible. It's going to be an absolute train wreck. Think through the problem first, okay? So, you go, okay, well, UG is mgh, and that's going to be some initial kinetic energy, which is 1/2 mv naught squared, equals 1/2 mv squared. And conveniently, you can cancel out all the masses, and if you multiply by 2, which you can, you just get that equation, okay? That equation comes from the idea that energy is conserved. And all that potential and kinetic energy at the top is going to equal a pure form of kinetic energy at the bottom. Okay, that's it. So now the trick here is that you have to find H. But you have that handy-dandy little equation that says H equals L times 1 minus cosine theta. And if you need that equation on the test tomorrow, I will give you that equation. Don't memorize it, okay? You just have to know how to use it. So, you know the length, you know the angle is 60 degrees, you can find the height. So, and this is going to be an important idea that you have to understand. So if this thing is moving like this on a pendulum, like this, and it's a certain distance up here, and it's already moving, when it hits the bottom, it's all going to be kinetic energy. Now, it's the exact same situation as if I just take this and I drop it. So, in terms of an energy perspective, whether I hold it up here and let it swing, or if I hold it up here and let it fall straight down, the energy is going to be the same, because that's all it has. It has a certain amount of energy up there, which is going to be the same energy down there. Now, the times are different, okay? To get from here on a pendulum is going to take longer than if it falls straight down, okay? It has to travel a greater distance, and the acceleration isn't 9.8 meters per second squared because it's on a pendulum. But more importantly, from an energy perspective, it doesn't make any difference. So whether I drop it or I let it fall on a swing on a pendulum, it's the same energy, okay? You end up with the same velocity. The times aren't the same, the accelerations aren't the same, but the energies are the same. So, you get down with 2c, you should get 4.02 meters per second, okay? Not 2.99, not 4.05, exactly 4.02. Now, at that point, it turns into a California problem. So imagine this thing is swinging down, it's going to hit a mass and then it's going to combine this, and then they're going to move off together. From now, you work it from a momentum standpoint and go, okay, so the momentum of 1 plus the momentum of 2 equals a new momentum of 1 plus a new momentum of 2. It's the exact same idea of momentum that we used in the last unit. Okay, it's nothing new, it's the same momentum. The bottom one is at rest. It's a California problem, so you can find V prime. Okay? So that answer on 2D should be a little bit less than 3 meters per second. Okay? Which should make sense. Oh, yeah, right. Okay? Well, I combine my masses. I have to have the same momentum. It's going to be moving slower. Okay, cool. Now, then on E, you want to figure out how much kinetic energy do you lose. So you have to calculate kinetic energy twice on E. You need to find the kinetic energy of that 0.5 kilogram mass by itself. And then, now that you know the velocity of the two objects moving off together, then you can find the new kinetic energy there. So you're going to use 1/2 mv squared twice. Once with the 0.5 kilogram mass moving at 4.02 meters per second, and then the combined mass moving at about 3 meters per second. And you're going to subtract those two kinetic energies. And your answer to 2E should be around 1 joule, a little bit more than a joule. So what that means is that when things hit and they move off together, you always lose some energy in the collision. Okay? You always do. You always lose energy in the collision because you have to make them stick together. Now, what I want you to see on F is now we're back to an energy thing. Oh, okay. So the combined energy of the two objects at the bottom is going to equal the potential energy at the top because the energy has to be conserved, right? So whatever energy you have at the bottom is the total amount of energy that you can have at the top. That's it, because energy has to be conserved. So at this point, you know the energy that they're going to have when they move off together. You found that on E. Now, if you're an equations kind of person, you can go, okay, the kinetic energy at the bottom is going to equal the potential energy at the top. Oh, that's 1/2 mv squared equaling mgh. So this is the beauty of working with equations. Your masses cancel out. You know what the velocity is, but use the velocity after they move off together. That isn't that 4.02. That's the velocity of the two after they've left. Okay? So you know that velocity. You know what g is. Find the height. Okay? So what that number tells you is how far they swing up. And that height is this vertical distance. So now, at that point, it turns into an algebra problem. So once you get that h, then you're going to go back to h equals L times 1 minus cosine theta. So you can take that h, okay, and put that in there, and then, which is going to be that height, and then you're still going to know the length of the pendulum. That hasn't changed. So then it turns into an algebra problem. So then you've got to get cosine theta by itself. So I hate negative signs. So I'd divide by L. I'd add cosine theta over here. I'd subtract that number back over there. And then at some point you've got to take the inverse cosine to get that angle. So if all goes well on H, you should get an angle around mid-40s. Okay? So you just got to work that step by step by step by step by step. Now on number 3, because if 3A is wrong, everything's going to be wrong. So on 3A, you need to calculate that moment of inertia. Your answer to 3A should be like 0.0144. Because if that's wrong, everything else is going to be a train wreck. So, your answer to 3B should be around 10, and your answer to 3C should be around 40. It's an ish, but it's somewhere in that ballpark. Okay, now let's talk about problem number 4, because I promise you there's going to be a satellite problem on the test tomorrow. I promise you. Okay, you mark my words. I promise you it's going to be there. So, now here's the other thing on number 4. Do not round these answers too much, okay? Because if you do that, then you're just screwed going forward. So, the first thing you got to realize that, okay, here's the satellite, okay? This is what we talked about yesterday. I'm going to put it in what's called it's called a barbecue roll. If you ever watched the movie Apollo 13, they actually talk about that. After the hydrogen and oxygen tanks explode and they're hurtling through space, that's what they'll talk about. It's okay, we got to get this thing into a barbecue roll. Because if you're not, you have one side of the spaceship gets just really hot, then the other side gets really cold, and that's a bad thing to happen, okay? So literally, you want to set this thing up like a rotisserie chicken so that you give an even heating all the way around. So, you got to take the revolutions per minute, change that into radians per second, and then use that radians per second to calculate alpha. So, your answer to 4A says 0.112 radians per second squared. Okay? That's wrong. Everything else is going to be a train wreck. Okay? So, you're going to use alpha equals omega minus omega naught over time. Your initial is 0. You're going to take those revolutions per minute, change that into radians per second, and then divide that by the time that's in seconds. And that's what you're going to get. Okay? Because if that's wrong, just everything's going to be a train wreck. Now, when you get to B, you're going to use the idea that torque equals force times radius equals I alpha. So at this point, you know what alpha is. Okay? You found that number. You're going to calculate the moment of inertia. Okay? Now, with this one, you're not going to use mr squared because it's not a point mass, nor is it a thin hoop. Okay? It's a solid cylinder. So we're going to use that 1/2 mr squared, and that's going to allow you to calculate the moment of inertia. And then you're going to know the radius, because you know the radius of the satellite. That's where those engines are. Now, the question asks for the force from each rocket. So the total force that you need should be around 80 newtons, which means if you divide that by 4, each rocket's going to need to provide about 20 newtons of force. So your answer to 2B should be around 20 newtons, okay? So, because obviously this satellite isn't going to spin on its own. You have to fire the rocket engines to make it begin to spin, okay? Now, when you get to 4C, you need the mass of fuel. And if you're an engineer, this is vital, okay? Because, you know, it costs money to get this thing up into space. So you don't want to overshoot it and go, oh, we're just going to call it 100 kilograms in each rocket. Well, that's going to add a lot of weight to that rocket to get it up into space. But you don't want to guess and just go, oh, we'll just call it, I don't know, 5 grams. That ought to be enough. Okay? But then if you don't send enough fuel, then the rockets don't fire long enough. Then you're not spinning fast enough, and you've just wasted a multi-million-dollar satellite because you can't do math, okay? So there's a balancing act. This is a number you have to get exactly right. So on C, and this is on your equation sheet, okay? This isn't something that is not there. So change in momentum can equal one of two things. Force times time equals mass times change in velocity. And that's what you all were used to thinking of. You are used to the mass remaining constant, and you're going to make something speed up or slow down, okay? Like, oh, here's the cart, right? I push in on it, I let go, hey, the momentum is changing. So you all were used to having mass remaining constant and changing the velocity, okay? Well, that's not how rocket engines work. Rocket engines work by kicking out gas at very high velocity, but that mass is being kicked out. That's how rocket engines work, okay? So for rocket engines, it's still force times time, but then it's the change in mass times the constant velocity, okay? So if you divide by t, you divide by t. So if you look at this, if you want a rocket engine to provide a lot of force, you want a big change in mass per unit of time. Okay? This is why rocket engines are so big. You want to expel a lot of gas per unit of time. Okay? You also want that gas to escape at a high velocity, which is why we heat it up. This is why we typically use like liquid oxygen and liquid hydrogen. If you've ever seen a hydrogen balloon go off, okay, it's a very explosive reaction. Produces a lot of heat and a lot of expanding gas. So if you want to create a lot of force, you need a big change in mass per unit of time, and you want those gases to leave at a very high velocity. So I gave you, this is the velocity of the escaping gas, okay? That number is in the problem, okay? You have this number. You know how much force that you need. You just found that. Oh, you need about 20 newtons of force. You know how much time the rocket engines are going to fire. Oh, 300 seconds. So the only thing you don't know is mass. So divide the velocity over here, so you know the force, you know the time, divide by the velocity, that's how much mass that you need. And that answer should be around 15 kilograms. So, then on D, you want to find the rotational kinetic energy. Oh, rotational kinetic energy is 1/2 I omega squared. You have everything to calculate this. You already found the moment of inertia up above because you needed that to calculate alpha, or I alpha. So you already have the moment of inertia. You know how fast it's spinning. You already found that up above. There's nothing new to find. All you're doing is plugging that in. Okay, that's it. It's a plug and chug type thing. So your answer to 4D should be something times 10 to the 5th. Okay, it's a lot of rotational kinetic energy. It's a really big satellite. Okay, so that's something times 10 to the 5th. Now, on E, they want you to calculate the work that's done by each engine. Now, here's the deal. There's two ways you can look at work. Fundamentally, it's a change in energy that also equals force times distance. Now, I can't do force and distance because this isn't like a linear thing. I'm not pushing the satellite. I'm making the satellite spin. So I can't do the force and distance thing. Okay, I can't do that. I can do the change in energy. So with this situation, the work that you're going to do is the change in the rotational kinetic energy. Oh, the satellite doesn't have any initial rotational kinetic energy because it's just here, okay? You're going to fire the engines and you're going to make it spin. Oh, now you're going to have rotational kinetic energy. So your initial rotational kinetic energy is 0. Your final rotational kinetic energy is your answer to D, okay? So the work that's done is your answer to D because that's the change in the rotational kinetic energy. But they want the work done by each rocket, so you basically, to get your answer to E, take your answer to D and divide it by 4. That's all you have to do because work equals the change in energy. Now on F, they want power. Power is work divided by time, okay? So you know your work because you found that on E. Divide that by however long the rocket engines fire, which is 300 seconds. There's your answer to F. So your answer to D is 10 to the 5th. Your answer to E is 10 to the 4th. And your answer to F is going to be around 140 watts. So it's going to go 10 to the 5th, 10 to the 4th, and then about 140. Now, on G, you want to calculate the kinetic energy of the satellite, okay? So you got to go old school on G. So you got to go back to the idea that the velocity of an orbiting satellite is big GM over R. Okay, so now you got to go old school. Okay? But remember, that distance has to be from the center of the Earth out to that satellite. Okay? So the first thing you need to do is calculate that velocity. And remember, that velocity should be something times 10 to the third. Okay? Any orbiting satellite has a velocity of 10 to the third. And then you're going to use, once you get that velocity, are you...
Okay. Yeah.
Hold on.
Can you just email me too?
Yeah, I can just email it to you. I'm getting them all off. Okay, all right.
See ya.
Okay. Okay. Anyway, so that velocity should be something times 10 to the third, and then your answer to G when you get done, using 1/2 mv squared, your answer to G should be something times 10 to the 11th. Okay? That's a lot of energy because it's going really, really fast and it has a really, really big mass. On H, you're going to find the orbital period. Again, that should be something times 10 to the third if you're in seconds. If you're in minutes, it's about 90. On I, you want to calculate the angular momentum. So on I, you're going to use L equals I omega. Now, this omega, okay, you have to be careful with this omega. This omega is not the omega that you found when it was spinning around on its axis. This is the omega in terms of how fast it's going in radians per second as it goes around the Earth. So this omega here, you're going to take theta divided by time. But that time is going to be your answer to H. Okay? Because that's how long it's going to take for one orbital period. So your answer to H is going to be around 5,000 seconds. That's an ish. Okay? So you're going to take 2 pi, divide that by about 5,000 seconds. You're going to treat it as a point mass, which is mr squared. And again, that radius is not the radius of the satellite itself. That's the radius from the center of the Earth out to where that satellite is. So if all goes well on I, you're going to get something times 10 to the 14th. So your answer to G is 10 to the 11th. Your answer to I is 10 to the 14th. That is a big moment of inertia. And then let's talk about number 5. I promise you there's going to be one like number 5 on the test. I promise you. So here's your setup. You've got a mass and it's going to roll down this hill. So again, this is going to boil down to energy. So milkman, when it sits up here, what's the only type of energy that it has?
Gravitational potential energy.
Oh, right? That's it. It's the only thing you have. Now, if it rolls down the hill, it's going to change into KT and KR. If it just falls off the back, it's just KT. Okay? But no matter what, you only have a certain amount of energy to start with. This is what we talked about yesterday. Elliot's uncle's estate is only worth so much money. Okay? The question is, does she have to split it with her sister, or does she keep all the money? Okay, that's it. That's the fundamental idea. Now, here's the trickiest part of this problem. Your KT isn't the issue. That's 1/2 mv squared. Okay? It's not a big deal. The tricky part is your KR. So that's going to be 1/2 I omega squared equals mgh. So the tricky part here is that you have to pick the moment of inertia that matches whatever object this is. So if you look on this, this is a solid cylinder, right? So the moment of inertia of the solid cylinder is 1/2 mr squared. But don't confuse this 1/2 mr squared, this 1/2, with this 1/2 that's out here, okay? This 1/2 that's out here is because of the equation of rotational kinetic energy. This 1/2 is here because it's 1/2 mr squared, okay? They're both 1/2, but understand they're not the same 1/2, if that makes sense, even though they're both 1/2, okay? Now, what do you have to do for omega squared? This is the most vital thing. What do you do for omega squared? Tanner,
V squared R squared.
put in v squared over r squared. Otherwise, you can't solve the problem. Okay? So then the beauty of this is your r squared is going to cancel out. Your m's are going to cancel out. And then you can combine your terms into a fraction. Okay? So I promise you, I want to put a problem like this on the test tomorrow. I promise you. The only thing that I can change in this entire process is this. Okay, this is it. This is the only thing that I can change. That's it. Okay? I can make it a solid cylinder. Oh, that's 1/2 mr squared. I can make it a sphere, 2/5 mr squared, or a tennis ball, 2/3 mr squared, or a thin hoop, it's mr squared. This is the only thing that I can change. And again, I beg of you, do not just sit there and go, oh, I'm just going to memorize this equation. Okay? It's a train wreck. Think through the process. Okay? Think through the process. Oh, right. It only has potential energy. Oh, it's going to roll down. It's going to have both forms. It's going to have translational kinetic energy, and it's going to have rotational kinetic energy. And these values added together here have to equal mgh. Now, here's what you cannot do. Okay? Listen to me. Here's what you cannot do on this problem. You're forbidden to do this. Okay? Absolutely forbidden. What you cannot do to find the linear velocity is just go, oh, I'm just going to use v equals v naught squared plus 2ad. My initial velocity is 0. I know the height of the plank, and I'm just going to find it that way. Okay? You cannot do it this way if it's rolling. You can only do this if all of that potential energy just boom goes into straight translational. Okay? So you cannot do this problem if it's rolling because it's rotational and translational, okay? You cannot just say, oh, I'm going to use this to find your velocity. You can do that if it just, boom, falls straight down. Then you can do that all day long, okay? But if it's rolling and moving down the hill, you cannot use this to find the velocity. You have to go through this process. So, what you should see on 5B, that linear velocity should be around 2.5 meters per second. Okay? Elliot.
So in that equation where you substitute all that, you can't, or the only thing you can cancel is the mass and the radius, right?
Yes.
But you keep the velocity.
Oh yeah, you have to keep the velocities. If you don't, yeah, you can't cancel out the velocities. Because you, number one, if you do this, Elliot, so you can cancel out the masses, okay, that's cool. So then you get 1/2 v squared plus 1/4 v squared equals GH. So what's 1/2 plus 1/4? I asked you this yesterday. Huh? Yeah. So you get 3/4 v squared equals GH. So then v is going to equal the square root of 4/3 GH. Then once you get v, then you can do a whole bunch of things with it. So, anyway. Now, on D, I asked you to calculate the velocity if it all goes into translational. So what you should see that your answer to 5D is bigger than your answer to 5B. Okay, so your answer to 5D should be around 3 meters per second. Your answer to 5B is around 2.5. Okay, but think this through. So what's happening on D, this is where Elliot gets all of the inheritance. Okay, she doesn't have to split it. Okay, so on D, all of that potential energy changes into translational. And mgh equals 1/2 mv squared. There's nothing, you're not losing energy, any energy to make it spin. So when you answered 5C, okay, about why there's a difference, do not talk about friction, okay? This has nothing to do with friction. This is about how the energy gets split, okay? So on 5E, oh, if you split it, you're not going to be going as fast. If you don't split it, then you can go faster. So it's like Elliot. If she doesn't have to split the inheritance with her sister, she can buy a really fast car. Okay, it's like, hello, Corvette. Okay, but if she has to split the money, hey, she got to settle for a Volkswagen Jetta. You know, still not bad. You know, but it's not a Corvette. So hopefully that gets you all through those problems. If you want to hold on to this assignment and hand it in tomorrow, you can, because there's going to be a lot of these problems on the test tomorrow. The test tomorrow is just going to be over energy, okay? It's not going to be like comprehensive. Normally there is, but with all the snow days and the testing and you seniors getting out early, I just don't have time. So the test tomorrow is just going to be over energy, okay? But there's still a lot tied into it. It's still, oh, it's a satellite problem. You still have to know torque. Oh, you still have to be able to calculate the velocity of the orbiting satellite, okay? But the vast majority of the test is just going to be over this energy stuff, okay? Anything else you want me to go over on that assignment? Going once? Going twice? Milkman.
Number 1.
Seriously?
Yeah.
I get this wheel spinning, right? Eventually, what's it going to do?
Slow down.
Why? What's going to make it slow down?
Look like there's not an outside force constantly acting on it.
Because there is or isn't.
Isn't.
There's no outside force acting on it. There's no friction. There's nothing like that.
Okay, goodbye.
Thanks. There's no friction on this making it slow down at all.
There is.
There's your answer.
Okay. Thank you, Mr. Brookhaven.
Not a problem. It's like, there's no outside force. Really? There's not friction? No. Really? Okay. All right. So let's talk about this. So this is a cool little deal. One of the many toys that I have. It's like, why do you teach physics? Because I get cool toys. Teaching math is boring, but if I call it physics, I get cool toys. Okay, so we can combine a whole bunch of different things in this. So this is a little steel marble, and this is a plunger, right? So I can pull this back. Now, when I push this back, am I doing work? When I pull this back, am I doing work? Rebecca,
Yes,
why?
because you're applying a force in a direction.
Fantastic. I'm applying the force over a distance. Now, this is a spring, right? So remember, when you have springs, and let's just do kind of a big comprehensive review. So when you do springs, it's force and elongation, and this is a linear function, okay? F equals kx. Force is on your y-axis. This is your compression. That's your spring constant. It's a linear function. This is just y equals mx, okay? So, now, here's what's going to be important. On a spring, what this means is that the farther I compress it, the more force it takes. So, what you cannot do is, with springs, to calculate the work that's done, you cannot just take force times distance, because I'm not applying the same force. I can use the idea that this is a triangle, I can find that area underneath it, but I can't just take force times distance because this thing is not a rectangle, okay? I can still use the same idea, but I have to treat it as a triangle and not as a rectangle. So I'm going to pull this thing back, okay? And I've stored potential energy. So I'm going to take this, I'm going to put this marble here, okay? Now, here's what's going to happen. There's a whole bunch of energy transformations that are going to take place. So I'm going to flick this switch, and Mother Nature doesn't like potential energy. So she's going to go, not digging it, boom, she likes kinetic energy. So that marble is going to get launched. It's going to hit inside this is what's known as a ballistic pendulum. It's going to hit that, and then this thing is going to swing up like this, and then we're going to be able to measure this angle. So they're going to move off together. So this is going to be like a California problem. So I'm going to store energy here. That energy is going to translate into the kinetic energy of the marble. The kinetic energy of the marble is going to hit the ballistic pendulum. This thing is going to swing up, and then we're going to store some potential energy up here. So there's actually a whole bunch of physics that happens just in this little dynamic, right? So we've done work, we stored energy in the spring, I flipped the switch, the potential energy changes into the kinetic energy of the marble, it does work, it exerts a force over distance, we increase the kinetic energy, it hits the ballistic pendulum, they move off together, it's a California problem. Oh, then we can measure how far it swings up. Oh, voila, now it's all potential energy at the top, okay? So, we'll do this, I'm going to set this kind of up here, so I'm going to do this, okay? And it swung up to a height of about 17 degrees. So, here's what I want to do. I want to work backwards, and I want to figure out the velocity of that marble when it got launched. Okay, that's what I want to do. So, I've got a pendulum, and that length is 0.23 meters. So that's the distance from here down to here, so I know my length of my pendulum. It swung up to a height, to an angle of 17 degrees. Now, just knowing this, if I know nothing else, I know this pendulum is 0.23 meters long, and it swung to a height of 17 degrees. At this point, we can use that new equation that says H equals L times 1 minus cosine theta. Okay? I can figure out the height that moved to when it swung up. Okay? Then once I get that, then I go, oh, that's potential energy. Oh, that has to equal the kinetic energy at the bottom. So Tanner, do us a favor. Take 0.23 times 1 minus cosine of 17 degrees.
Zero point zero one
0.01
zero zero.
meters. Okay? That's about a centimeter, right? So it really didn't go up all that high because it only swung up to like a height of 17 degrees. So here's what's going to be important conceptually. Whether I take that marble and I lift it up straight up to a height of 1 meter or 1 centimeter, or I make it swing on a pendulum, it's still going to store the same amount of potential energy at that height. The path it takes doesn't matter, okay? So it's going to be lifted to a height of 1 meter. So it's going to have the same amount of UG, whether I swing it in an arc or I let it fall. The times are completely different. That's not the same. But the pure change in energy is the same. So, here's the deal. So, when you do this, you have to work energy first. There's a sequence. You have to do the energy thing first. So basically, the UG at the top is going to equal the kinetic energy at the bottom. So when that marble hit that and it moved off like this, it's just like that pendulum problem that you all just worked. The kinetic energy at the bottom has to equal the potential energy at the top. Okay? That's energy has to be conserved. That's it, right? So this is going to be mgh. This is going to be 1/2 mv squared. Now, here's the trick. Is this mass the mass of the marble, the mass of the pendulum, or is it the combined mass? Yankee,
Come on.
why? Your answer is right.
Because it's. I don't know. Let's see.
What is, articulate this. This is right,
They're
but
both going
articulate
together.
it. Huh?
They're both moving together.
Yeah, because that pendulum isn't going to swing until the mass of the marble hits it, okay? The pendulum isn't going to, oh, it's just starting to swing on my own. No, not so much, okay? So this mass is the combined mass. Now, the beauty of it is, because it is the combined mass, and they're the same, oh, we can cancel those out. How cool is that? So those masses cancel out, okay? And I get 2gh equals v, square root of that. So Tanner, Mr. Calculator, take 2 times g times that height of 0.010 meters.
0.197.
So call it 0.20 meters per second. Okay, not very fast, but I can just, that's about 0.20 meters per second, okay? Not very fast. Now, this is what you have to understand. That's the velocity of the two objects moving off together, okay? That's the velocity after they've hit and moved up. So this is like a California problem. Now, what I want to find out is how fast the marble itself was moving before they moved off, okay? Because that's ultimately what I'm trying to find. And this is what's known as a ballistic pendulum. And this is actually how they calculate the velocity of rifles, of bullets. They'll shoot a bullet out of a rifle, and obviously you can't sit there and go, boom, start, stop, as that bullet travels across because it's going too fast. So what they'll do is they'll have a setup like this. They'll shoot the bullet into a block like this. It will swing up. They'll measure how fast that was going, and then they'll work backwards and find the velocity of the bullet. Okay, and that's how they're going to get this number. So we've done the energy side. Okay, you have to think this through. It's like the alphabet. You're going to do energy first, and then you're going to do momentum. Okay, so you do energy first, then you do momentum. So, with that said, we know how fast they were going. So now we're going to go momentum of the marble plus the momentum of the pendulum equals the new momentum of the marble plus the new momentum of the pendulum. Okay, it's nothing new, it's a momentum problem. Oh, okay. But Tanner, they moved off together, so what can I do over here?
The California problem.
Yeah, I can factor out that velocity, right? So this is going to be the mass of the marble plus the mass of the pendulum times V prime is going to equal the mass of the marble times the original velocity of the marble. So all this is a momentum problem. Ah, Mr. Burkamp, we can do that all day long. So that 0.02, what is it, 0.2 meters per second? Is that what we've got as a velocity? That's that velocity here, okay? That's how fast it had to be moving at the bottom to swing up to that height, okay? That's how fast it had to be going. So that's that velocity. So if you plug in the numbers, so we're going to get this by itself, so we're going to divide by the mass of the marble. So the mass of the marble is I'm trying to read upside down. 8.38 grams. The mass of the pendulum is 86.2 grams. We're moving at 0.2 meters per second. And then we're going to divide by the mass of the marble of 8.38 grams. Now, I know from the beginning I've preached to you this has to be in kilograms. But as long as you leave everything in grams, it's still going to be the same answer. Yeah, you can divide everything by 1,000 and get it into kilograms. At the end of the day, it's still going to be the same ratio. This just saves you this hassle. So that's 8.38. So somebody take Tanner, take 8.38 plus 86.2, multiply that by 0.2, and then divide that by 8.38.
2.28.
2.28?
Yeah.
So 2.3 meters per second. So that's how fast the marble was moving before it hit the ballistic pendulum and then moved up like this. Okay? I promise you there's going to be one like this on the test. There's a question like this on the review. Okay? I promise you. Because it combines so many things. Okay? You work it like the alphabet. You do energy first, and then you do the momentum. Okay? You have to work it in that sequence. Now, here's what you're tempted to do. You go, oh, Mr. Burkamp, can we just, and this is a legitimate question, it's like, if we know how far we compress the spring, we know how much energy we store here. Then doesn't all of that energy that you store here have to equal the energy that's in the pendulum when it swings up? It would seem reasonable. Oh, hey, Burkamp, you've been preaching that energy is conserved. And I have been. Okay? And energy is conserved. But here's the problem. The reason that we can't do that is because anytime two objects hit and they move off together, you lose some of that kinetic energy in that collision. So this is why I can't set the energy stored in the spring equal to the energy that's up here, okay? Because they hit and they move off together. Now, what I could do, okay, is if I said, okay, hey, I'm going to launch this spring. So what I could do is, if there wasn't like a collision involved, what I could do is say, okay, hey, I'm going to store some energy in the spring. Then once I launch it, that's all going to change into the kinetic energy, the marble. And then if I have that marble like roll up a hill, then that would equal the potential energy of the marble up the hill. Okay, and I promise you, you're going to have a problem like this. It's going to involve an elephant named Babar. Okay, promise you. Look for Babar the elephant. Okay, I'm going to tell you straight up. It's going to be Babar. And we're going to start with some type of energy. It's either going to be kinetic, it's going to be energy in a spring, Babar is going to be up a hill, something like this. And on that problem, I'm going to tell you, or tell you right now, and I'm going to tell you that in the instructions. That problem, you have to set up a chart, okay? If you don't set up the chart, I'm not even going to grade it, okay? So on the Babar the elephant question, you have to set up a chart, okay? All right, so let's talk big ideas. So let's say that you're going to have two situations. Let's do three situations. Okay, so imagine this. You have three situations. Situation number one, you have a cart and you're just gonna drop it, and it's just gonna fall straight down. Okay? Situation number two, you're gonna have a cart at that exact same height, but you're gonna let it roll down a frictionless ramp. Okay? Situation number three, I'm going to take that cart of that same height, but then I'm going to launch it as it goes off. Okay? So I drop, I roll, I launch. Okay? Those are your three options. Of those three, which one's going to have the most energy to start with? Okay, so let's label them A, B, and C. Which one of those three is going to have the most energy at the beginning? Ray gun. Or are they all going to be the same?
They'd all be the same.
Why?
Because they all start from there.
No. That one's not. That one's launched.
Oh,
C is
then
launched.
C,
Why?
because it's launched.
So it's going to have,
More energy than the others.
why?
Because it's less of the kinetic energy pushing on it.
And
The potential energy.
caused by?
Gravity.
Okay. So this C is going to have UG and KT. What's the only type of energy A and B are going to have? Yeah, these are just going to have UG. Okay? So, which ones are going to land with the greatest speed? A, B, or C? Which one's gonna land with the greatest speed? Yankee.
C,
Why?
because it's gonna, has more, kinetic energy going with it, like,
Keep going. You're fine.
versus like A. It's
What's the other
like
type of
same
energy
amount.
A has?
Uh,
What's the other type of energy B has?
kinetic.
No. B only has what type of energy initially?
Oh, potential.
Yeah. A and B only have UG, right? That's all they have. C has UG and
Kinetic.
kinetic. So this is Elliot's uncle. Hey, he's got $5,000. Elliot's uncle. Hey, he's got 5,000. This one, it's Elliot's uncle and aunt, and they've got more money because they have both forms. So this would be like 10,000. Okay. So which is going to allow Elliot to have more money at the end of the time? A, B, or C?
C.
Why? More money to start with, right? So since that has more money to start with, it's going to land with more money. Okay. Will A and B land with the same velocity? Milkman.
No.
Really? Why?
Yes, they will. Yes, they will.
Why will they land with the same velocity?
Because B is frictionless, so that means they both only have a.
So these both start with the same type of UG, so therefore they're going to land with the,
Same connect.
yeah. So these two are going to land with the same speed, which will be less than that one. Now here's the last and final question. Which of the three will take the longest to reach the ground? A, B, or C, or will they all take the same amount of time?
They'll all take the same, I mean B.
Okay, there's a big difference, Kate, between all take the same. No, it's B. So let's talk A and C. Will A and C both take the same amount of time to hit the ground? Yes, right? This is projectile motion. Oh, whether I drop this thing or I shoot it out horizontally, they're both going to take the same amount of time. Okay, because horizontal velocity isn't part of the equation. B is going to take the longest for two reasons. The acceleration is going to be less because it's sliding on an inclined plane, and it has to travel the greatest distance. So C is going to land with the same velocity that A has, but it's going to take longer to get there because it's going to have a smaller acceleration but over a greater distance. Okay, so test tomorrow is going to be mostly multiple choice, but there's also going to be some big complex problems that you have to work out. There's going to be a bar problem, elephant, okay? I promise you, it's going to be there. It's going to have, you're going to have to set up a chart, you're going to have kinetic energy, you're going to have UG, and you're going to have energy in the spring, okay? Promise you. There's going to be some version of this of that satellite problem, okay? Not as big, as complex as the one that's on your assignment, but there's going to be some version of the satellite problem, okay? If there's the pendulum problem, I will give you that equation that H equals L times 1 minus cosine theta. I promised you there's going to be something about that ballistic pendulum problem. Work it first as an energy, and then do momentum. And all of these problems are on the review, okay? All of the types of problems you're going to have to do in one version or another are on that review. So, okay.